Okay, so now we have two more lightning sessions, and these ones are with the really hot off the press research. We're going to start with a talk that was supposed to be given by Jibang. Unfortunately, he couldn't make it, and due to COVID restrictions, and now Haifeng Xu will give the talk from Chicago. We're sorry we couldn't have Jibang, but thanks so much for being so flexible. The talk will be about optimal coordination and generalized principal agent problems, a revisit and extension.
Hello, can everyone hear me? Okay. So hello everyone. I'm going to present optimal coordination generalized principal agent problem. This is a joint work with Jiarui from Oxford, my PhD student at UVA, Minbiao, and Jibang, and I'm Haifeng. So yeah, unfortunately, Jibang got COVID, so he cannot come. He gave me the slides this morning, so I'll try to interpret what he says. Yeah. Okay. Actually, I want to start by saying this is actually not a paper. This is really like a 2 or 3 page note. So, but I thought it probably still interesting to present because some of the modeling idea and the message I thought would be quite interesting to present to this audience. So the work starts by kind of a beginning of this year. We're trying to kind of think about a unified framework that can somehow capture a bunch of kind of leader-follower problems, including Bayesian persuasion that I used to work a lot, and Stackelberger games, which is another setup I have been working a lot as well, and then the contract design. So I was thinking whether there's a kind of general model that can capture this. We spent quite a bunch of time to see what would be the most basic setup that can capture all the models and still kind of interesting enough to study. And we spent quite some time until at some time we realized that this problem actually already considered by Mylson, which is, he titled it, called it Generalized Principal Agent Problem. And I'm going to show you the model here, but this is really just abstraction of the contract design problem that I have seen multiple times in this morning. So there's a principal and agent. The agent has a private type theta that is drawn from some prior distribution everyone knows. And also the agent is going to take some action A that's not observable to the principal. It's a private action. And then the game starts by the agent can report a type theta prime, maybe a misreport to the agent, to the principal. And then the principal is going to pick a strategy X to play. And then after that, the agent is going to take his own action A. And to see this captures the contract design problem, this X is exactly the contract you're going to design. And then the agent is going to take action after your contract. And this is also a Bayesian persuasion problem because X is a signaling scheme. And then the receiver is going to best respond to your scheme. After agent take action, the principal get a utility depends on his own strategy, agent's action, and the agent's type. And the agent gets some utility. For now, especially for Mylson setup, you should think of this strategy X as discrete. That's what his original paper is about. Think of X as there were 100 different possible X. So what is a coordination mechanism that coordinates their behavior? Well, it's basically the following pi, which basically takes any reported agent type theta prime as input, and then with the probability pi xa, so the principal is going to himself take action X, and then recommend the agent to take action A. So that's kind of the coordination mechanism. Mylson's paper basically showed that there's a revelation principle for this. There exists an optimal and truthful coordination mechanism. That's Mylson's result. And actually, it's surprising. And in this case, we get the honest report and obedient action recommendation. And surprisingly to me, Mylson actually came up with a linear program that can solve this optimization problem in his paper as well. You don't need to look at the detail of the program, but really what's it doing is just try to maximize the principal expected utility subject to truthfulness and the feasibility constraint. So everything is nice, and this time complexity is going to be polynomial depending on the number of principal action, agent action, and the types. But this is going to become a problem if you think of if this X is in a continuous space, for example, the signaling scheme, or for those two contract design, or the possible contracts that you can pick from. What we do, because he's already coined this generalized principle, we somehow slightly more general, but we're really just barely a little bit more general. We assume that the strategy X is a convex set. So it's not discrete, it's a convex set. And both functions are linear. Actually, we can do slightly more general than linear, but I think for the talk, it's kind of more easier to be linear. And that's all we did. So this is the so-called more. That's it. And so why we care about this, as I mentioned, this turns out to capture a bunch of problems that I have seen before. Contract design, normal form stack-burger game, Bayesian persuasion, depends on what you pick as the X. OK? But in this problem, the previous LP doesn't work because the LP depends on how many X there are, but there are infinitely many possible X. It turns out that we're able to prove a kind of a slightly revised version of the principle, revelation principle. That is, there always exists an optimal direct coordination mechanism that is truthful and succinct. Succinct in a sense, for this pi, if you fix the action recommendation and the type report theta, pi only support on at most one strategy. Okay? And the proof is actually quite simple. This is the standard revelation principle argument. And in this case, we can actually represent this succinct mechanism mathematically with the X and pi. It turns out that using this characterization, we can revise original Mileson's program into a kind of a convex program. Basically, I'm not going to do his pi XA recommendation. Instead, I'm going to directly use this X as a strategy. This is not a convex program yet, but it turns out that you can convert it to a convex program, and that can be solved efficiently. So why this is interesting? Well, it turns out that it implies the computability of many randomized things. In particular, this randomized contract that is computable in polynomial time, where we have seen multiple times in today's talk, this turns out to be just a corollary of the previous result. And this significantly simplified the proof that was by Matteo before. I talked with Matteo actually during the conference. He actually realized this recently as well. So this kind of, it turns out the proof is basically just a convex program. And moreover, it also implies the optimal mixed strategy for Bayesian stackable equilibria, optimal signaling for Bayesian receiver in persuasion problem. So that's it. I think the only takeaway I wanted to give is randomization turns out to indeed ease the coordination between principal and agent.